following. So here I'm given an exponential equation. I want to solve this, and so to solve this, seeing how these have different base, we're just going to take the log of both sides. So here I'm going to take the log of 7 to the 3x equals to the log of 3 to the 2x plus 6. Is that what I have here? Okay. So with that, exponents can get moved up front to be multiplication. So this is 7ln plus, oops, 2x plus 6 ln of 3. All right, so here we just move everything, oops, multiply that. So here I just move it all to one side. So here I have 3 ln of 7 times x. Because remember, ln of 7 is just some number, and ln of 3 is just some number. And so this be minus 2 ln of 3, right, minus x, equals to 6 ln 3. And then here we can just factor out the x. So here I have x of 3 ln 7 minus 2 ln 3 is equal to 6 ln 3. That means x is equal to 6 ln 3 over 3 ln 7 minus 2 ln 3. And the reason I choose natural log, you can use any log, but the reason I choose natural log is just the least amount of characters I have to write when I work through this. And then what do I do here? So I want it rounded to 2 decimal places. So go ahead and just jump this through a calculator, and I'll do that with you. All right, so we'll have, yeah, I don't even remember. We'll have 6 ln 3 divided by the quantity of 3 ln 7 minus 2 ln 3. That's fine. And so decimal approximation, so about 1.81. Okay. 1.81. And to be honest, you can check yourself, and I would suggest checking yourself. So what do we have? We had, what was the original one? 7 to the quantity of 3x equals 3 to the quantity of 2x plus 6. Gee, that gives a really weird. Hey, 1.81. Yeah, that's weird. But it is the same. Okay, so just hit when it gives you this weird exact result right here. Oops, go back forward. Just hit it. It'll give you something weird exact form. Just click approximate form, and that's just a way of checking it. Okay, so you do need to show all the work, but it's good to check it. All right, so let's do this. Student takes out a loan of interest rate of 130,000 at a rate at 6.7 for a year. So we're going to do 4 years. Please be careful that you check this. It should, sometimes I write 4, sometimes I write 5. Be very careful. So how do we do this? Let's open up the, where's my notes? Notes. Note me. I know I did this. Take notes. I did this in 3.2. Is this 3.2 stuff? I think it's 3.2 stuff. Where did we do this? Maybe we did in 3.1. I know we did this. That's not a little crazy. No. Do we do it in 3.3? Do you remember what section we did this in? 3.4. Okay. Hi. it is. Thank you. Okay, so we're done it there. All right, so here we have compound interest and continuously interest. So we're going to be using these two formulas. All right, so here our principal for this case will be, I'll go ahead and just rewrite these formulas for you so you have them on these papers. So here are the principals. So the amount per time 4 is equal to the principal of 1 plus r over n times nt. And then for the continuous one, it's going to be the a of t is equal to p of e to the rt. All right, so let's do this. So our principal in this case is 130,000. So 130,000. And here we're going to let n be, so we're going to do it annually, so that'll be n equal to 1. We're going to do it again where n equals monthly, so that'll be n equals 12. And then we'll do it again for continuously. So the amount after 4 years, so 4 is the amount of years, so I have principal times 1 plus the rate. The rate here is 0.067. Please convert this rate into a decimal. If not, you're going to get weird numbers. We're going to put a 1 here, and then we're going to put a 1 times 4. And just for simplicity's sake, I'm going to write out both and then calculate both. And so here, the monthly one would be for 12. So I have 0.0067 over 12. And I'm going to do this 12 times 4. Okay. And so here you just plug in using this formula. All right, and we'll just grab this. Hi, Mr. Wolfram Alpha. All right, so 13, 130,000. All right, times 1 plus 0.00067 divided by 1 raised to the power of 1 to the 4. Oops. 1 times 4. And here we get 168,050. Let's go ahead and write that down. 168,500, and just go ahead and just do the 44 cents. So just round it to the nearest cent. It'll be fine. And once we type it in like that, it's really easy to type in the 12 because you just put a 2 here and a 2 here. Ta-da! And so here we get 169,082.8 and 49 cents. Just go write that in. So 169,828 and 49 cents. And then the last one here, go ahead and plug this in. So this is equal to 1,300. Or 130,000, sorry, e to the 0.067 times 4. I'll go ahead and plug that in. And it should be really close to these numbers. If they're not really close to those numbers, you did something wrong. All right, so just get rid of this, put an e here, and we just put in 0.067. And here we get 169. 995, 1. Making sure the rest of the number are you? All right, so it doesn't show you the rest of the number. So we'll just round to the nearest thing. As long as you're within like $1, I'm not gonna. Or you should be fine. I'm not horribly worried about where you round this. Okay. Any questions on these first two? Nope. Okay, let's go on. Let's keep moving. All right, so here we want to find the inverse of this function. So the inverse of the function, I do this for you in, I think this one is in 3-1. 3, 1 is this. I think it's 3, 2. Right, my cube. Here it is. Da, da, da. All right, so how to find an inverse. So you're going to set it as y, interchange x and y, solve for the equation for in terms of y, for y in terms of x, if possible, and then rewrite this. And so let's do that. All right, so here we're going to write this as y equals minus x minus 3 over 3x minus 4. So that's step 1. Step 2, we're going to swap our x's and our y's. So we'll have x equals minus y minus 3 over 3y minus 4. And then step 3, we're going to try to get this in terms of y. The way I do that is just multiply this across. And then go over here. So I'll have 3yx minus 4x equals minus y minus 3. We'll move all the y's to one side, so I'll have 3yx plus y equals 4x minus 3. So here I'm just moving this over here and this over here. Factor out the y, so I'll have y equals y times 3x plus 1 equals 4x minus 3. And then here we have y equals 4x minus 3 divided by 3x plus 1. And then here for step 4, we just write f inverse of x is equal to 4x minus 3 over 3x plus 1. Okay. Does Wolfram Alpha know how to do this? I think it does. So let's just test. Let me see if I can figure out if it does. So let's find f of x in inverse function. There we go. Yeah, I know what it is. Can you calculate it? I don't remember if it's been calculated or not. I should have pre-tested this. Oh, fine. I'll let you guys watch me futz for 2 seconds because I think you guys want to know how to double check it on the calculator. I could be wrong. 3x minus 1. Find f. I want to see if it's smart enough to do what I want. Let me just type in inverse. Oh, hey. Look at that. That's how you do it. What section is the inverse function? The inverse section here is in 3.2. So 322. It's on page 3 of that section. Okay. And if you want to check it in, apparently all you have to do is type in inverse in your function, and this will pop it out for you. So here we can just double check. Did we get this right? Yep, we got this right. Okay. All right, let's go to the next page. Let me just export this. File. Oh, hi. That's why I was like, none of these look right because you're not in the right program. I'm just going to export this right here. You can go ahead and hit close. And we don't need to save it. We've exported it. All right, let's do the next one. Oops, don't need another layer. There we go. Go ahead, zoom on in. All right, so here, let's see what happens here. So here, I want to find the limit of this. So here, if I just plug it in, real quick. So if I just do a quick plug in, I get infinity over infinity, right? And so this is a point where we can use L'Hopital's rule. So here we have the indeterminate form. So this is indeterminate. And so we'll go ahead and say, so the limit of x approaches infinity of x over is equal to its derivative. So what's the derivative up top? Well, here's a quick question. What's the derivative of 3 to the x? You guys remember this? Remember how to do this? Dx of 3 to the x. I forget which one section. This, of course, shows log when it should be ln. So remember that 3x prime is equal to 3x times the log of 3. So the log of whatever inside. That way, because remember, if it's e to the x, ln of e, the log of e is just 1. So this ends up being 1. But if it's not, this is what it looks like. And we're going to need that here. So here we're going to do this. So we're going to take the derivative of the top minus. So the derivative of the top will be, we'll leave the x, and we'll take the derivative here. So this will be 3x ln 3 plus, here will just be 3 of x all divided by, the derivative here of the bottom is 3x ln 3, right? Plus the 1. So, oops, I forgot my limit, didn't I? It's always working in Photoshop, right? The limit as x approaches infinity. All right, so what do we have here? So what can I just decipher from here? So here I can do something. Well, let's go ahead and pull out the 3x, right? So let me do a little bit of math. So this is equal to the limit as x approaches infinity of 3x, because I have it on both top and bottom, 3x ln of 3 times x plus, or x ln 3 plus 1. All right, does everyone see how I took out that 3x? Because now I can cancel the 3x safely. What happens up here? This goes to infinity, because x here is going to go to infinity, right? And then this is just going to stay 3, so this overall goes to infinity. All right. And then we can always double check using Wolfram Alpha. So let's do that. So here I want second limit. All right, let's just do this. X goes to infinity. All right, x goes to infinity. And here we're going to have on top x 3 to the x. And then on the bottom, we're going to have x minus 1. And this goes to infinity. And so that matches what we, oops. What you do here? No, hold on. Here we go. This matches what we got. Okay, so please check it. How did I get plus? Oh, okay, here I'm using product rule, right? So here I'm using product rule. And so it'd be, I keep this one constant, and then I take the derivative of this one, and then here I take the derivative of x. The derivative of x is just 1, then 3 to the x. Does that make sense? So here I have f of f equal to x and g equal to 3x. So this would be f g prime, and then this is f prime, which would be 1 g. And then here we know what this is. This is just this, and the 1 goes away. Okay, perfect. All right, so that's the end of this one. So let's do the next one. All right, so you're going to have some optimization problem. Please, for this one, you're going to have to show that it is indeterminate, right? It's in indeterminate form. Take the derivative, show you did the derivative, and then show some sort of algebra or whatever to get you to whatever conclusion you get to. Okay. All right, for this one. So we want to have a box with a square base with an open top, must have a volume, must have this amount of volume, so 32,000 cubic centimeters. Find the dimension of the box, which leads to the least material used. You should have had a problem like this on the homework, but let's just go ahead and run through how I would do it. All right, so we have a solid line here, box. Line to, and then this goes in, this comes in, this comes in. Or actually, you should be able to see this line. All right, and so we have a square base, and so here we have length times width times height, but I know that L and W are the same, so I am just going to use A for both, right? So because I have A, and H. So the volume of the box is equal to A times A, since it's A squared times H. And I know what that volume must be. That volume must be 32,000, and we'll go ahead and leave out the centimeters, because we know. We'll just leave everything in centimeters to make life easier. Then we have the surface area, right? The surface area, or the amount of material used for that. So we'll have one base, because it's an open top, so we only have one bottom. So that is just A squared. And then we'll have the 4 sides, 1, 2, 3, 4. And each of those are A times H plus 4AH. All right, and what do we want to minimize? We want to minimize A. We want to use the least material as possible. Okay, so since we only have one H here, in my mind, it's easier just to solve this for H. So this implies H is equal to 32,000 divided by A squared. Yeah, and so we'll just plug that in. So we have A equals A squared plus 4A times 32,000 A squared. We'll simplify that. So that'd be A squared plus one of these A's cancel one of those A's. 4 times 32 should give me 2,800. Yeah, that seems right. Over A. Okay. Then we want to find its derivative. So here we're going to take derivative here. So I'll get 2A. Here we're going to have 1 plus. So here we have A. So derivative of 1 over A is negative over 1 over A squared. And so here we'll have minus 128 over A squared. We set that equal to 0. The easiest way to solve that in my mind is just multiply A through. So if I'm going to solve this through, I'm just going to multiply everything by 2A. So I have 2A cubed minus 128. It's called clearing the fraction. You may or may not have been taught that technique. And then here we just move it over. So I have A cubed. I'm going to divide this by 2. So that's 64,000. And the cubic root of 64,000. So I know what the cubic root is. 64. Yeah, I want the cubic root of that. Wahoo. It's 40. Okay, so we're going to say here A is equal to 40 centimeters. A is equal to 40 centimeters. So now what we want is the dimension of the box. So we know what A is, so all we have to do is find out what H is. So H would just be 32,000 divided by 40 squared. Just plug that in. All right, so we have 32,000 divided by 40 squared is 20. And so H is equal to 20. And does that match what we previously did with a different problem? Sure, your homework problem, you did something this, and 90% of the times you have an open top box with a square bottom. Your base of your box, or the A, will be twice as what your H is. Just a good thing. All right. How did A become squared again? Oh, it's because it's the bottom of the box, right? So the bottom of the box is a square. So it states it's a square. So the bottom of the box, here I have A, here I'll have A. Because normally your volume equals your length times your width times your height. But I'm just saying L equals W. And so I just set that equal to A. So I have A times H. And so here, and so when I plug that in, I get 1A up here divided by 2 A's down here. So this just gives me a single A. And then when I take its derivative, I get this. And then in order to solve this, I'm multiplying everything by A squared. So I multiply everything by A squared. So 2A times A squared is A cubed. This times A squared just gets rid of the bottom. 0 times A squared is that. Okay? So that's how I get, and it's just a way of throwing, it's called clearing the fractions. Okay. And any other questions from this one? Oh, how did I get the other equation? Okay, so the other equation just comes from the surface area. So how much material do I need to use to make the bottom of the box? Well, the bottom box is just A by A, so I need A squared worth of material. And then for each of the 4 sides, I'll have 1A times H. So this is A times H. And also this side would be A times H. This side would be A times H. This side would be A times H. I have 4 of them, so it'll be 4AH. I have no top. It's an open top, so I don't need to worry about that. Okay. So for A cubed, you multiply it. Oh yeah, so here I have this equation right here. And I don't like dealing with fractions, and so you just multiply everything by A cubed. So 0 times A cubed is 0. This times A cubed is, not A cubed. You multiply everything by A squared. This times A squared is, well, the A squared is just canceled this. 2A times A squared is 2A cubed. It's just a way of, if you have, it's a way, what's it called? It's called clearing the fractions. So if you have exponents in the fractions, or variables in the fractions, you just multiply the equation by all the denominators, and it gets rid of it. Okay. All right, so let's do the last problem. I don't want to have enough time to do that. All right, what equation do you plug in to find H? I use this one. I know what A was, and I just plug that in there. Okay. Okay. No. Okay. You will see something like this on the. You will see something like this when you actually take the exam. I can almost guarantee it. So it's good you ask all the questions you have on this now. All right, let's go ahead and export this. Okay. All right, let's just do this last problem here. All right. So let's look at this. So here we're going to use the steps outlined in 4.4, aka find all this stuff in this order. All right, so let's start with this. So let's start with the domain. So the domain of this function, this is something raised to a power. This is something raised to a power. Do I have this written backwards? I think this should be, I think I want this to be 3 halves. I'm sorry, I think I want this to be 3 halves. Just because it just makes things easier. All right, so here, what is the domain of this? Well, you know what my honest suggestion is, and I'm going to do this. I'm going to do this just so we have it up to look at the whole time. Is my honest suggestion is graph it first in a computer and then work out why it should look like that. I mean, so let's go to Desmos real quick. Desmos. There we go. All right, so we have 5 raised to, no, we have x raised to the 5 power. And then we have minus 5x raised to the 3 half power. Is this what I wanted? Somehow this doesn't look like what I wanted. Did I want it the other way? Hold on. I pulled this from the homework. Let me double check. I pulled this from the homework. Let me double check. Hi, book. Ah, that's what this is. This is not. Let me make 1. That's supposed to be a 3. This is problem 24 from the homework from 4.4. I just grabbed one because I thought I'd use the book because I thought they might make an interesting program. Now that I have the correct one, let's do it. All right. So notice here that we have here 3 here, and this is 2, 3. Wow. This is what I want because it has interesting things here. Because this would show me it does not exist. Here's another 0 and all this other stuff. So here, let's just look at this for a second. So here the domain is everything. And here I can kind of explain why the domain is everything. So here we have the domain. The domain for this one is all real numbers. And why is it all real numbers? Because if this is a cubic root, remember cubic roots can accept any, it's all reals because the root here is odd. And so odd roots can take anything. Right? So the root here is odd. You don't need to explain it, just tell me what the domain is. In this case, it's all real numbers. All right, let's find the intercepts here. So let's do the intercepts. So the intercepts, how do we find that? First one we plug in, let's find in the x-intercept. So here if we plug in x of 0, that'll give us our y-intercept here. Where does intercept y when we plug in x equals 0? So x equals to 0 is 0 to the 5/3 power minus 5 times 0 to the 5/3, or the 2/3 power. Well, what's the answer here? Well, the answer here is, of course, 0. And so we have one of our intercepts at 0, 0. The other intercept we want to find, the other way to find intercepts, so these are the vertical intercepts, so aka where, so these are the vertical ones. The horizontal ones is where it intercepts the x-axis, and so that's where it's equal to 0, right? That's where it's equal to 0. So we have 0 of x to the 5/3 minus 0. And we'll just crunch through that. Now, do you guys know how to solve cubic stuff? And the answer is no, right? So just use a calculator. Yours will not contain all the funniness that this one might, but I wanted to show you a funny one just to be, that way you can be comfortable in what you find. So here we have 0 equals x to the, x to the power of 5 divided by 3 minus 5x. So we know what one of the answers is. One of the answers is 0, right? The other answer should fall out. So we have 0 and 5. So 5 is another answer. So here, this implies x is either 0 or 5. And so here we get the two intercepts of 0, 0. So that's the same one here. And then we get the other intercept of 5, 0. All right. Symmetry, there is no symmetry here, so symmetry none. Just write none. There's no symmetry here. This isn't even or odd or anything special. It's just what it is. It's not periodic. The next thing we want to talk about is asymptotes. So no vertical asymptotes. We just want to kind of find n. And so in this case, we just want to know what the n behavior is, asymptote. So here we're just going to take the limit as x goes to minus infinity of x to the 5 third minus x to the 2 thirds. And here it goes to minus infinity, and limit as x goes to positive infinity of x to the 5 thirds minus 5x to the 2. That's going to just go to positive infinity. All right, but we do have 2 points. Let's go ahead and graph these 2 points. We have a point here, and then 1, 2, 3, 4, 5 point here. All right, so what's the next thing we want to find? We want to find the local minimaxes. So how do we do that? We take our derivative. So we need to take a derivative of this. So the derivative of this would be 5 thirds x to the 2 thirds minus, and then this 2 thirds would pop out, so 10 thirds x to the minus 1 third. Okay, so we have this. What do? We set this equal to 0. Because then we want to find our critical points, or we set it equal to non-existent. Okay, so notice here, and in fact, let me, before I even do this, let me rewrite it real quick, just to make our lives easier. So we have 5x to the 2 thirds. No, let's not do it that way. Yeah, let's go ahead and do it this way, minus 10. And then we're going to write 3 cubic root of x. And the reason I want to do this is because it makes it really clear. So we want to find where this is 0. And we also want to find where it does not exist. Well, where does it not exist? Well, it doesn't exist where x is 0, right? Because here, if x is 0, this breaks. So x equal to 0 is a critical point, right? Then we just want to find where it equals to 0. Well, for something this complicated, I wouldn't worry about solving it. I would just go ahead and let Desmos do it. Or not Desmos, but go ahead and let this do it. So here we're going to have, I'll just cheat. I want to see how smart this thing is. Hey, be smart for me for a second. Where's the derivative equal to 0? It should tell me. Two. Okay. Now let's plug that in. That's the cubic root of x, yes. So it'd be 1 over the cubic root. Let me clean that up for you real quick. This is 1 over. So this is 3, and this is the cubic root. So it'd be the little 3 over this on x. Okay. And so the other point here is 2. All right, so let's look at this. So here we're going to go from minus infinity to 0, from 0 to 2, and then from 2 to infinity. We're going to look at our sign on f prime, and then we're going to say if it's increasing or decreasing. So let's go through this. All right, so let's look at this. If f of x is, say, negative 10, this term's going to win, and it's going to be negative. And so this one would be negative minus or plus. Hold on. See if I can do this correct. I don't want to lie to you. Let me rewrite this real quick. Hold on, let me explain why this term is always going to win for the large values. So for large values, 5 x to the 2/3 power is equal to the cubic root of x squared, right? And so this will always be for very large values, say 100, this term, since it's the highest power, will win, and it's always going to be positive. So for both this one and this one, it's positive. Here, if I plug in 0, well, I can't plug in 0, but if I plug in 1, right, I'll get 5/3 minus 10/3, it's negative. And so here I have it negative. And so what I can say here is I have it increasing for here, decreasing for here, or you can just plug in a number. You can just plug in like -5 and just have a calculator calculating. And just all you care about is the sign, remember? So it's increasing, decreasing, increasing. So here I have a local. Here it's going from increasing to decreasing. So here I have a local max right here. And then here I'm going from decreasing to increasing. So I'll have a local min. Okay. And so here we have established both our intervals of increasing and decreasing and local max and mins. Last thing we want to do is concavity. In order to do that, we want to find f of x double prime. So here we're just going to take this and do it one more time. So here a 2/3, so this becomes 10/3 as the 2/3 pops out. X to the minus 1/3. And then here this will be, I'll have another negative, so this becomes positive 10/9. And then this will be to minus x to the minus 4/3. Okay. All right, so here we have the double root, and we're going to set this equal to 0. All right. And we're also going to want to, where does it exist? This x does not exist at 0 again, right? So notice x does not exist at 0 because of the same reason here. This would go down below. We're not allowed to have that. Same thing for this. So this at 0, I dividing by 0, so x is 9. Does this equal 0 anywhere? Well, let's find out. And here, so let's see if I can have it do it for me. All right. Yeah, it writes it that way. That's fine. Be cute about it. Anyway, so let's just type it in. So it'll be 10 divided by 3. Oh, did I mess something up? Yes, I did. I forgot my 3 here. So this should be 9. This should also be a 9. Okay. Sorry about that. Let's go back to our little problem. And this is the same thing as we have here, but let's go ahead and just type it in the way we had it. So this is to the minus 1. And here we have plus 10 divided by 9 to the minus 4. I'm going to set that equal to 0. All right, so here's our second derivative. We set that equal to 0. -1. And this is assuming a complex value root. All right, so let's put in the -1 real quick. Okay, so here we have our 2 solutions. And the reason why the -1 makes sense, because notice here this is, let me kind of show you why this -1 makes sense real quick. Yeah, we only got 5 minutes. Just assume it's true. All right, so where we're going to go from? We're going to go from -infinity to -1. from -1 to infinity. Oops, -1 to 0, and then from 0 to infinity. All right, and so in this case, I honestly suggest just giving yourself test numbers, right? So instead of doing this, we're just going to test some numbers and see what happens here. So here we have this, and so we're going to test. So from -infinity to 1, let's just test, I don't know, -5, right? Oops, that's not what I wanted, -5. And then here we'll put in -5. So here I'm just testing some number within that range. Thank you. Thank you for your awesomeness. Like some imaginary number. Of course. Couldn't you just tell me what the real part is? Uh-oh. Yeah. Assuming principal root. Hold on, let me zoom out. Why is this so zoomed in? I didn't think it would get this bad. So here are the real parts. And so we're going to have this. Hold on. Let me see something super quick. The rest of it I can give you because at 0, from 0 to infinity, since we're in the positive realm, it is always positive. So it's always concave up. Hold on. Let me double check something real quick because I don't want to lie to you on the practice. Where am I at? Nope, 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 nope. Okay. Be that way. Oops. Because the answer here is anything negative is complex. Because this is complex, this is complex. Hold on, let me simplify this and I can get to a real answer. So I know this part. Let's just do everything up to this point real quick. So this part is positive. The cubic root of -5 should give me negative. Hold on. Let me simplify this. All right, so 5/9, 10/9, since those are the same, it doesn't matter. Here, we're going to take this, we're going to move this here. I'm going to do. Let's do this in parts real quick. Why is this still giving me? That's what I want. I don't want. It's being smarter than it wants to be, and I don't want it to be that smart. I want to be dumb. That's my problem, is I want it to be dumb. Because it should be this. Hold on. I'm going to force it to be more done. So this is positive. I promise you, you don't have it this bad. I give you whole numbers. Hold on. This is positive. Ah, here we go. So this is positive, this is positive. If you force it to be less than this. So this is always concave up. So all of this is concave up. Okay. And yet we know we have a min, max, and all this other stuff. So let me put it together, and then we'll be done. So here it's concave up. Here it reaches a max. It's concave up. Here at -2, I'm at a local min. So somewhere around here, I'm at a local min. Concave up. I know I go through this point. So here's a max, here's a min. This is concave up and concave up. If I have a concave up, local max looks like that. If I have a concave down, local minimum looks like that. So this and goes up. And that should match what we drew.